Let's try another example, and this time we're going to stack weights on a table. So let's draw some table. Let's put some weights on it. Say we got a big weight. Let's pick a different color. I didn't really like that color. All right, so we got a stack of weights on here. Let's say the first one is 50 pounds. Let's say the second one is 40 pounds. So we clearly got some force of gravity pushing down on this table. And if the table's not collapsing and the weights aren't falling, then we have some counteracting force fighting it. And we call this the normal force. So we'll call that Fn. And they're countering each other out. Or I should say canceling each other out. Or another way to put it is balancing each other out. So let's go ahead and write this out. What's the force of gravity? So we got a force going down. That's force of gravity. And that's equal to 40 plus 50 is 90 pounds. And if the force of gravity is 90 pounds and it's not breaking, if it's not falling, the weights aren't going through the table, then the normal force countering it also has to equal 90 pounds. Because math. So what we get is the sum of all forces. Well, that's just what? The force of gravity equals the force of gravity plus normal force. And this whole thing is just equal to 0, basically. It has to. Or in other words, the whole system is in static equilibrium. So now let's increase the weight. Let's draw another table. And let's draw those same two boxes on top. So what? We got the 50-pound one, and we got the 40-pound one on top of that. And let's draw an even bigger one. So this one was 50 pounds. And this one was 40 pounds. And let's make this one on top. Let's make it big. Let's make it 100 pounds. Make it way bigger. So if we increase the force of gravity, if we increase this to, well, 50 plus 40 is 90 plus 100 is 190. So the force of gravity is 190. And that looks nicer. If we increase this to 190, then the normal force also has to equal 190. So F of n is equal to 190 as well. And this is true as long as this thing isn't breaking. As long as everything is holding, then the normal force has to be the opposite of the force of gravity. And this isn't just true for normal forces. This is true for all reactionary forces. If the sum of all forces equals, or if all the forces are canceling out, if they are literally canceling out, which means things aren't breaking, things aren't accelerating, so the sum of all forces are 0, and that's what that means. If they're all canceling out, then the sum of all forces have to equal 0. They have to cancel out, or we are in static equilibrium. So let's do one more example, and actually let's go ahead and do the exact same example, just add a little bit more weight to it. So let's go ahead and just copy this and move it over to here. It's the exact same example. And actually, you know what? This is probably a bad idea, because in this example, something different is going to happen. So let's go ahead and draw the exact same example then. So we have the 50-pound weight. We have the 40-pound weight on top of it. Then we got the 100-pound weight on top of that. And let's add one more weight. Let's call this last weight 3 pounds. And the other ones are clearly the same. This one is still 100 pounds. And this one is still 40 pounds. And the bottom one is still 50. So now we have an even bigger force of gravity over here. And it adds 3 pounds, so the force of gravity would be 193 pounds. So if this was in static equilibrium, then the normal force would clearly be 193 pounds. But let's say that the structure of the table can't handle that kind of pressure. Well, then there'd be a big crack. It would break. So in this example, as you can clearly see, the sum of all forces clearly do not cancel out. They do not equal 0. So they are not in static equilibrium. So the main idea I want you to take away from this is if the sum of all forces don't equal 0, then it's not in static equilibrium. And you can tell whether or not there is a reactionary force canceling out your initial force.